Hey everyone, so we're going to do an example of fitting a set of data with a least squares line. The data that I have today is the temperature averages in October in Los Angeles, California. These are actually the average highs for October in degrees Fahrenheit. So we have all the way from 2010 to 2019. This is my data set. What I'm going to start off by doing is just define two variables. This variable year is just going to be the first column. This is just kind of extracting the data a little bit. The year will be the first column of my data set, and this variable temperature, or temp, will be the second column of my data set. Okay? So if I run this section and I display the year variable, it's exactly just holding all of the years that I have for my data. And the temp variable is holding all the temperatures. Okay, so that's just the first thing I wanted to do with this data set. Okay, so let's visualize the data and get a sense of what we're trying to do. So I'm going to plot year on the x-axis and the temperatures on the y-axis. I'm going to make the marker size slightly bigger than the default just so that it's easier to see, as well as the line width. Okay, so I'll run this section. So here's what my data looks like. You can see on the x-axis we have 2010 to 2019. On the y-axis it goes from about 76 to 85. It looks a little bit scattered, like spread out a little bit here, but I'm just going to change the limits of my y-axis to show you that it's kind of all localized between 10 degrees, really. So if I just make my y-lim, my limits on the y-axis to be 70 to 90 maybe, and I run this section. Now when the limits are a little bit more spread out, you can see that it's kind of following a linear path. It seems to be increasing on average each year. You know, between two subsequent years it might go down or it might go up, but on average it seems to be following this trend. Okay, and we want to find a line that describes the behavior of this data and kind of captures what's happening over time, more or less like on average how the data is behaving. And that's the least squares line. I'm not going to go over why we're computing it in this way, so I'm just going to more or less show you how to do it in MATLAB. So what we're going to start off by doing is we want to find m and b. Remember, m is the slope of the line that we're trying to find. B is the y-intercept. If you have those two pieces of information, you can draw a line. And the way we're going to find m and b is by solving this system of equations. It doesn't really look like a system of equations right now, but this is the A transpose times A times the vector mb, so those are our unknowns. And then our right-hand side is A transpose times the temperature vector. A quick note here, this A caret T, this is not the MATLAB syntax for A transpose. This is more of the mathematical syntax of like how you would see it in a textbook. You would see A to, it looks like a power almost. So that's why I've written it that way here, but I'll show you how to actually compute the transpose in MATLAB. So this is the system we're trying to solve. And the way we're going to do it is create an augmented matrix with this A transpose A on the left, A transpose times the temperature on the right, and then do reduced or echelon form on the augmented matrix. So the first thing I need to write down is, what is A? The matrix A is going to be that first column, the years, concatenated with ones. So I'm going to make ones column vector that's the same size as year. So A looks like this. Okay, so first column is the years, the second column is just a bunch of ones. And the reason for this is that, remember that our line going through our data has the years on the x-axis and then the temperatures on the y-axis. So this is saying 2010 times m plus b is going to equal some y value. Okay, so this is the coefficient matrix for m times x plus b. Okay, so the first column are representing the coefficients on m, and the second column are the coefficients on b. All right, so A is not quite the matrix that we want to do reduced or echelon form on, The matrix that describes our system, or the augmented matrix, it will look like A transpose A and then A transpose times the temperature. So I'm going to call this maybe least squares matrix, LS mat. This is A transpose times A. Remember in MATLAB, a transpose can be computed just by putting this little apostrophe here. And then we have A transpose times the temperature. This is our augmented matrix. Okay, and if I put this in the command window, you can see that it's a 2x3 matrix. This is representing 2 equations and 2 unknowns. And the way that we're going to solve this is the way we usually solve systems of equation, which is doing reduced echelon form. So the solution, I'll just call it LS sol for the solution, is going to be reduced echelon form, RREF, on our augmented matrix. So when I put that in the command window, it looks a little bit strange because, we should have a 1 here. We actually do. This is 0.001 times 10 to the third power. It's in scientific notation. So this is a 1, this is a 1, and this value is our M, this value is our B. So we need to extract those from the matrix. So I'm going to say M equals LS sol. I want the first row last element. That'll give me my M. B is going to be the second row last element. So that'll be my B right there. So when I run this, I get M and B. It looks slightly different. That's just a rounding issue with how this is displayed. It's not really a different number, so this is correct here. Okay, the next thing I want to do is plot our least squares fit, or y equals mx plus b, with our data to kind of visualize how our least squares fit is capturing our data. Okay, so let's take a look again at our figure. The x values we have go from 2010 to 2019. So I want to make sure that the line y equals mx plus b that I'm about to plot goes from 2010 to 2019. So I'm going to create this vector x from 2010, maybe a step size of 0.1 to 2019. And then y, my least squares line, is going to be m times x plus b. Okay, and then in order to plot this line with my data, I'm going to use the command hold on, and then plot xy. I'll plot a red line, the line width of 2. So if I run this command, my figure is still up, it's just hiding behind my MATLAB, so I'll pull this up again, and we have our data and our least squares line. So you can see our line is kind of tracking a general trend of our data, a linear trend. Okay. So this is the least squares fit. So we computed, we solved this linear system of equations. So A transpose A times MB equals A transpose times the temperature. We did reduced echelon form, and then we extracted the slope and the y-intercept. One other thing we can do is compute the residual, we'll compute the residual and the least squares error. So the residual is just the difference, so let me actually bring up my figure again. It's the difference between the actual values, so these data points, and our predicted value, which is our least squares line. So for 2010, the actual value is 81, but our line predicted, for 2012, the actual value is 81. Our line is predicting 78, so or 78.96. So the difference between those two values is the residual. And the difference, all of those difference put into a vector is the residual vector. So this will be the true values, the temperatures, minus our predictions, which can be captured by capital A times the column vector MB. Okay, so these are our residuals. And the least squares error is kind of a measure of the length of the residual vector. Not quite, it's more like the length squared, but it's the sum of the squares of the elements in the residual vector. So our least squares error in this case is 58.0242. And that kind of tells us how close we are to the points in a sense. So this is how you do a least squares fit in MATLAB. I'll bring up the figure one last time. And if you have more questions, you can always email me or come to office hours.